In this lesson, we are going to solve another interesting problem on binary search tree. And the problem is, given a node in a binary search tree, we need to find its in-order successor. That is the node that would come immediately after the given node in in-order traversal of the binary search tree. As we know, in in-order traversal of a binary tree, we first visit the left subtree, then the root, and then the right subtree. Left and right subtrees are visited recursively in same manner. So for each node, we first visit its left subtree, then the node itself, and then its right subtree. We have already discussed in-order traversal in detail in a previous lesson in this series. You can check the description of this video for a link to it. In-order implementation will basically be a recursive function, something like what I'm showing in right here. There are two recursive calls in this function, one to visit the left subtree and another to visit the right subtree. Time complexity of in-order traversal is big O of n, where n is number of nodes in the tree. We visit each node exactly once, so time taken is proportional to number of nodes in the tree. I have drawn a binary search tree of integers here. Binary search tree, as we know, is a binary tree in which for each node, value of nodes in left is lesser and value of nodes in right is greater. Let's quickly see what will be the in-order traversal for this binary search tree. We'll start at root of the tree. Now for any node, we first need to visit all nodes in its left, and then only we can visit that node. So we will have to go left. Basically, we will make a recursive call to go to left child of this node. For this guy, once again, we have something in left. So we will make another recursive call and go to its left child. Now we are at this node with value 8, and we will have to go left one more time. And now for this node with value 6, which is a leaf node, we have nothing in left. So we can simply say that its left subtree is done, and hence we can visit this guy. Visiting for me is reading the data in that node. I'll write the data here. And now for this node, there's nothing in right as well, so we can simply say that its right is also done. And now we are completely done for this guy. So recursive call corresponding to this node will finish, and we will go back to call corresponding to its parent. If we will come back to a node from its left child, then it will be unvisited, because we can't visit a node until its left is done. So when we are coming back to 8, 8 is unvisited. So we can simply visit this node, that is, read the data in this node. When I'll visit a node, I'll paint it in yellow. And now there's nothing in right of this node, so we can simply say that right is done. Now we are done with this node, so call corresponding to this node will finish, and we will go back to its parent. Once again, we are coming back to the parent from left. So the parent, that is this node with value 10, is unvisited. If we would come back to a node from right, then it would already be visited. So I'm visiting 10, and now we can go to right of 10. So far we have visited 3 nodes. We first visited node with value 6, and then we visited node with value 8. So 8 is successor of 6, and then 10 is successor of 8. Now let's see what will be the successor of 10. For nodes with values 6 and 8, there was nothing in right, so we were unwinding and going to the parent. But for a node, if there would be something in right, that is, if there would be a right subtree, then its successor would definitely be in its right subtree, because after visiting that node we will go right. Now at this stage we are at this node with value 12. For this guy we will first go left, and now we are at node with value 11, which is a leaf node. There's nothing in left, so we can simply say that left is done, and we can print the data, that is, visit this node. So in-order successor of 10 is 11. Now for node with value 11, there's nothing in right, so we will go back to its parent, and now we can visit this guy. So after 11 we have 12. There's nothing in right of 12, so call for this guy will finish, and we will go to its parent. Now we are coming back to 10 again, but this time from right. So this guy is already visited, so we need not do anything. We can simply go to its parent, and now we are at this node with value 15. We are coming from left. This guy is unvisited, so we can visit it, and now we can go to its right. We will go on like this. Successor of 15 would be 16, and after 16 we will print 17, and then after 17 we will print 20, then 25, and the last element would be 27. So this is Inorder traversal of this binary search tree. Notice that we have printed the integers in sorted order. When we perform Inorder traversal on a binary search tree, then elements are visited in sorted order. Now the problem that we want to solve is, given a value in the tree, we want to find its Inorder successor. In a binary search tree, it would be the next higher value in the tree. But what's the big deal here? Can't we just perform Inorder traversal, and while performing the traversal figure out the successor? Well, we can do so, but it will be expensive. Running time of Inorder is big O of n, and we may want to do better. Finding next and previous element in some data could be a frequently performed operation. And good thing about binary search tree is that frequently performed operations like insertion, deletion, and search happen in big O of h, where h is height of the tree. So it would be good if we are able to find successor and predecessor in big O of h. We always try to keep a tree balanced to minimize its height. Height of a balanced binary tree is log n to the base 2, and big O of log n running time for any operation is almost the best running time that we can have. So can we find Inorder successor in big O of h? I have redrawn the example tree here. Let's see what we can do in various cases. What node would we visit after this node with value 10? Can we deduce this logically? Well, if you remember the simulation of Inorder traversal that we had done earlier, then if we have already visited this node, then we are done with its left subtree, and we have read the data in this node, and we need to go right. Now in the right subtree, we will have to go left as long as it's possible to go. And if we can't go left anymore, like here, there is nothing left of this node with value 11, then this is the node that I'm visiting next. So for our node, if there is a right subtree, then Inorder successor would be the leftmost node in its right subtree. In a BST, it would be the node with minimum value in its right subtree. I would say this is case 1. In this case, all we need to do is we need to go as left as possible in right subtree. In a BST, it will also mean finding the minimum in right subtree. Leftmost node will also be the minimum in the subtree. Now this is one case. Our node here had a right subtree. What would be the successor if there would be no right subtree? What node would we visit after this node with value 8? This guy does not have a right subtree. If we have already visited this guy, then we have visited its left and this node itself. And there is nothing in right, so we can say that right is also visited, but we have not found the successor yet. Now where do we go from here? Well, if you remember the simulation that we had done earlier, we need to go to the parent of this node. And if we are going to the parent from left, which is the case here, then the parent would be unvisited. For this node with value 10, we just finished its left subtree and we are coming back. So now we can visit this node. So this is my successor. Let's now pick another node with no right subtree. What would be Inorder successor of this node with value 12? What node would we visit next? Now here, once again, we do not have a right subtree for this node, so we must go back to its parent and see if it's unvisited. But if we're going to the parent from right, if the node that we just visited is a right child, which is the case here, then the parent would already be visited because we are coming back after visiting its right subtree. This node must have been visited before going right. So what should we do? Now the recursion will roll back further and we need to go to parent of 10. And now we are going to 15 from left, so this guy is unvisited. So we can visit this node and this is my successor. If the node does not have a right subtree, we need to go to the nearest ancestor, for which given node would be in its left subtree. Here for 12 we first went to 10, but 12 is in right subtree of 10, so we went to the next ancestor 15, and 12 is in left of 15, so this is the nearest ancestor for which 12 is in left, and hence this is my in-order successor. This algorithm works fine, but there is an issue. How do we go from a node to its parent? Well, we can design our tree such that node can have reference to its parent. So far in most lessons we have defined node as a structure with 3 fields, something like this. This is how we would define node in C or C++. We have 1 field to store data, and we have 2 pointers to node to store reference or addresses of left and right children. Often it makes a lot of sense to have 1 more field to store the address of parent. We can design our tree like this, and then we will not have problem walking the tree up using parent link. We can easily go to the ancestors. But what if there is no link to parent? In this case, what we can do is we can start at root and walk the tree from root to the given node. In a BST, this is really easy. For 12, we will start at root. 12 is lesser than value in root, so we need to go left, and now we are at 10. Now 12 is greater than 10, so we need to go right, and now we are at 12. If we will walk the tree from root to the given node, we will go through all the ancestors of the given node. In-order successor would be the deepest node or deepest ancestor in this path, for which given node would be in left subtree. 12 has only 2 ancestors. We have 10, but 12 is in right of 10, and then we have 15, and 12 is in left of 15, so 15 is my successor. Now let's use this technique to find successor of 6. We will first walk down from root to this node. 6 is in left for all the ancestors, but deepest ancestor for which 6 is in left is this node with value 8. So this is my successor. Remember, we need to look at ancestors only if there is no right subtree. For 6 there is no right subtree. Okay, so the algorithm looks good. Let's now write code for this. In my C++ code here, I'm going to write a function named getSuccessor that will take address of root node and address of another node, for which we need to find the successor, and this function will return address of the successor node. We could design this function differently. Instead of taking pointer to the node for which we want to find the successor as argument, we could just take the data as argument, and for this data, for this element, we can find the successor node and return its address, and that's why the return type here is struct node asterisk, because we will be returning address in a pointer. Or what we can also do is we can return the element itself, the successor element itself. We can implement with any of these signatures. Let's implement this one. We will pass the data in current node, and we will return back the address of the successor. Now the first thing that we need to do is we need to search the node with this data. I'm going to make call to a function named find that will take address of the root node and the data and will return me pointer to the node with this data. If this function returns me null, that is if the data is not found in the tree, we can simply return null. Else we have the address of the current node in this pointer to node that we have named current. Now in a BST, this search operation will cost us big O of h, where h is height of the tree. Search in a BST is not very expensive. We could have avoided this search if we would have passed address of the current node instead of passing the data as this second argument. But let's go with this. Let's now find the successor of this node. If this node has right subtree, that is if the right subtree is not null, we need to go to the leftmost node in the right subtree. I have declared a temporary pointer to node here, and initially I've set it to current.right, and with this while loop I'll go to the leftmost node. While there is something in the left, keep going, And finally, when I'll come out of this loop, I'll have address of leftmost node in the right subtree, and I can return this address. This particular node will also be the node with minimum value in right subtree. I'll move this code in another function. I have written this function named findMin that will return node with minimum value in a tree or subtree. In getSuccessor function, I'll simply say return findMin, and I'll pass the address of right child of current node. So basically I'm passing the right subtree here. Okay, now let's talk about case 2. If there is no right subtree, what we need to do is we need to walk the tree from root till current node, and we need to find the deepest ancestor for which current node will be in its left subtree. What I'm going to do here is I'm going to declare a pointer to node named successor, and initially I'll set it as null, and I'll have another pointer to node named ancestor, and initially I'll set this as root. And with this while loop, we will walk the tree till we have not reached the current node. To walk the tree, we will use the property of binary search tree, that for each node, value of nodes in left is lesser and value of nodes in right is greater. If data in current node is less than the data in ancestor, then first of all, this ancestor may be my Inorder successor because the current node is in its left. So what we can do is we can set this guy as successor, and we can go left. While traversing, if we will find a deeper node with this property that current node will be in its left subtree, then successor will be updated. Else, if the current node lies in right, we simply need to move right. When we'll come out of this while loop, successor will either be null or it will be the address of some node. Not all nodes in the tree will have a successor. Node with maximum value will not have a successor. After coming out of this while loop, we can return the successor. So this is my getSuccessor function, and I think this should work. You can find link to complete source code in description of this video. Overall, time complexity of this function will be big O of h, and this is what we wanted. We wanted to find successor in big O of h. Here we are already performing the search in big O of h. Finding minimum will also take big O of h, and walking the tree from root to a node in BST will also take big O of h. So overall, this is big O of h. If you have understood this code, this logic, then it should be very easy for you writing function to find Inorder predecessor. I encourage you to write it. I'll stop here now. In coming lessons, we will solve some more interesting problems on binary trees and binary search trees. Thanks for watching.